Hi everyone, I'm Po-chun from National Taiwan University. I'm here to present our work as the first author. The title of our paper is WG-WaveNet, Real-Time High-Fidelity Speech Synthesis without GPU. So, let us begin. Recently, neural network-based models have achieved state-of-the-art performance in many speech tasks like text-to-speech, voice conversion, and speech separation. These models are typically composed of two parts. The first part is a task-oriented model that conducts the speech tasks and generates acoustic features like spectrogram or F0 frequencies. The second part, referred to as a vocoder, is a generative model or a heuristic method generating speech samples from acoustic features. In this work, we aim to propose a lightweight vocoder for real-time synthesizing high-fidelity speech. The first neural network used as a vocoder is WaveNet, an autoregressive model that generates an audio sample at time t, given samples before it. The AR architecture makes WaveNet capable of generating high-quality audio, but the iteratively synthesis process also leads to extremely slow speed at inference time. Some non-AR vocoders were proposed to improve the efficiency. One is WaveGlow. WaveGlow is an invertible model. During training, real speech is used as the input, and the goal is to maximize the likelihood of the real data using the output and a given probability distribution, a normal distribution here. At inference time, a random noise is sampled from the distribution as the input. The model then can generate high-quality audio samples in parallel. WaveGlow is a very deep model and contains a large number of parameters. Also, big batch size is necessary for model convergence. Hence, it consumes huge computational resources during training and inference time. Another non-AR approach is parallel waveGAN, a GAN-based neural vocoder. As a lot of you may have known, there is a generator and a discriminator in a GAN. The discriminator is trained to distinguish real and generated speech. The generator is trained to fool the discriminator. Parallel waveGAN also utilizes losses on the frequency domain to improve the generator, though the generator is much smaller compared with WaveGlow. During training, big computational resources are still required to optimize two models simultaneously. The defects above motivate us to design a new vocoder. The model should be lightweight enough and use less computational resources. Also, this model should be capable of synthesizing good speech in real time. We refer to our model as WG-WaveNet. Given a random noise Z, WG-WaveNet generates speech conditioned on the Mel-Spectrogram. The model is non-AR for high-speed synthesis. Here are the two components in it. For being lightweight, we first apply a highly compressed WaveGlow model. And to further improve the speech quality, we add a non-AR WaveNet-based post-filter. We start with compressing WaveGlow. The WaveGlow model consists of several transformations to progressively map speech data to Gaussian space. Each transformation contains an invertible 1x1 convolution layer and an affine coupling layer. In the affine coupling layer is a series of calculations including a WaveNet-like module. There are 12 transformations in WaveGlow, means there are 12 WaveNet-like modules. The overall model is huge and hard to train. We apply cross-layer parameter sharing to reduce parameters and make the model more compact. In this compressed WaveGlow, transformations share the same affine coupling layer. As mentioned above, these transformations are processes gradually map the input from real data distribution to normal distribution. The input and output distribution of each transformation might be different. Hence, the invertible 1x1 convolution layers remain different across transformations. Now we have a compressed WaveGlow. This model is trained using the same loss function as in the original WaveGlow. We denote it as LZ. During inference, the model generates speech given a random noise Z sampled from the normal distribution. Though the computational cost is much less for the compressed WaveGlow, it still takes a lot of time to converge. We propose to use a WaveNet-based post-filter to overcome this problem. The post-filter can not only enhance the speech quality, but also shorten the training time. This post-filter is trained to optimize the losses on the frequency domain. The loss function, LS, is the multi-resolution STFT auxiliary loss in parallel wave gain with a little modification. For a target speech and a generated speech, we first extract the spectrograms of them, and then calculate the distance on the frequency domain. We can extract spectrograms with various frequency and temporal resolutions, using different parameters for STFT. So far, the loss is identical to the original. To make LS more representative to human perception, we also calculate the distances of the Mel-Spectrograms. We have introduced WG-WaveNet and the two components in it. During training, the loss LS is calculated using the generated X-hat and real speech X, and the loss LZ is calculated by maximizing the likelihood of the real speech X. The final loss function, L-total, is the combination of LZ and LS. Here lambda is a scalar. Note that in practice, we do not calculate LS in each iteration. We found that this setting gives a better result from our experiments. The two components in WG-WaveNet are simply trained together, that is, end-to-end training. In our experiments, we compared the proposed WG-WaveNet with four neural vocoders: WaveNet, WaveGlow, SqueezeWave, and parallel wave gain. To see the efficiency of different models, we first evaluated the speed and memory usage during training and inference. All the environments were set to the same. The second experiment evaluated the quality of the generated speech. Also, we evaluated the ability of generating high-fidelity speech. In the last experiment, we combined different models with a Tegatron tool to evaluate the performance as vocoders. We start with speed and computational cost. For WaveNet, WaveGlow, and SqueezeWave in this and the following experiments, we used pre-trained models from public implementations. Parallel wave gain was trained following the original paper. In WaveGlow and WG-WaveNet, the input is reshaped to groups of A samples. Inspired by SqueezeWave, the input of G20 is reshaped to groups of 20 samples. This makes G20 a faster version of WG-WaveNet. We show the numbers of parameters of different models. The cross-layer parameter sharing methods obviously make WG-WaveNet much more compact. The compact architecture results in much less GPU memory consumed while training, and with the help of the post-filter, the model can converge in less than 4 days. Although we did not train WaveGlow and SqueezeWave, the usage of GPU were reported in the original papers. We can see that WG-WaveNet is much more economical. For inference speed using only CPU or GPU, we can find that the autoregressive model is much slower than non-autoregressive models. The speed of 0.1 kHz means it takes about 10 minutes to generate a 3-second audio clip. All the non-AR models achieve real-time synthesis with GPU, while only the proposed WG-WaveNet and SqueezeWave make it without GPU. The next experiment is audio quality comparison. The AR model, WaveNet, has the highest MOS, which is much closer to that of the ground truth data, and there is a performance gap between the AR and non-AR models. The MOS of WG-WaveNet is close to the best non-AR model, parallel WaveGain. And WG-WaveNet is faster than parallel WaveGain. While considering both the MOS and inference speed, we found that the MOS decreased rapidly when the generating efficiency improves. Among these models, WG-WaveNet has a faster speed with good speech quality. This indicates the proposed WG-WaveNet can greatly increase the efficiency while preserving the speech quality. We plot the MOS and CPU inference speed of different models on a 2D plan. Only WG-WaveNet and SqueezeWave are capable of generating 22 kHz and 44 kHz speech in real time, and WG-WaveNet reached a good balance between the speed and MOS. Since we've shown that WG-WaveNet can generate 44 kHz speech in real time, the next experiment is the quality analysis on high-fidelity audio generation. We first compared recordings sampled at different rates, and found that sampling rates significantly affect perceptual results. The results of parallel WaveGain and WG-WaveNet are quite disappointing. We try to fix this problem by studying the effects of different parameters for extracting Mel-Spectrograms. In the previous experiment for generating 22 kHz speech, the FFT size, hop size, and window size for SDFT are 2048, 200, and 800. For an audio with 1200 samples, the extracted spectrogram contains 3 frames. Here is frame 1, frame 2, and frame 3. For 44 kHz audio signals with the same duration, the number of samples doubles. In this case, the parameters also double to extract spectrograms with the same number of frames. Here is frame 1, frame 2, and frame 3. So, for extracting Mel-Spectrograms for 44 kHz audio signals, the parameters double to keep the same temporal resolution. Another method is simply keeping the same parameters as in the 22 kHz case. With the parameters, we have frame 1, frame 2, frame 3, and so on. Note that we skipped some signals in this figure. Finally, we got 9 frames in this spectrogram. As you can see, keeping the same parameters increases the temporal resolution. These two different parameter sets are denoted as W1600 and W800. Now let's back to this table. We've shown that the results of W1600 parameters are not good. The W800 parameters in our experiments unfortunately doesn't improve the performance of parallel WaveGain. But when it comes to WG-WaveNet, the MOS is improved and close to that of 16 kHz recordings. Finally, our fastest WG-WaveNet reaches 4.01 MOS. Again, we would like to mention this model can real-time generate 44 kHz speech without GPU. The last experiment is text-to-speech. The MOS test shows that WaveNet still outperforms other methods, but the performance gap between AR and non-AR models narrows. WG-WaveNet has a comparable MOS and faster inference speed. This indicates the advantage of WG-WaveNet as a vocoder for fast, high-quality speech synthesis. In this work, we propose WG-WaveNet, a fast and lightweight vocoder which is capable of generating high-quality 22 kHz and 44 kHz audio samples faster than real-time without GPU. Last but not least, here are some useful links for anyone that is interested. And that's all. Thank you for your attention.